The paper provides a comprehensive overview of various approaches to word segmentation in Asian languages, focusing on Chinese, Korean, and Japanese. It highlights the significance of word segmentation as the initial step for many NLP tasks and its challenges due to the lack of explicit word boundary delimiters in these languages. The authors introduced 3 different methods for each language, ranging from least accurate to most accurate, along with their advantages and disadvantages. In the case of Korean, the main challenges arise from the high level of sparsity in Korean phrases and sentences. To address this issue, one study utilized a dependency grammar for parsing tasks, similar to the dependency grammar used to parse English. However, this approach has drawbacks, such as incorrect dependency relations during parsing. To overcome these problems, the authors introduced various dependency constraints, including having dependents precede heads, ensuring that dependency grammars cannot cross, and that every verb cannot have more than one subject and object. For Chinese, the authors discuss different approaches such as statistical dependency parsing and a hybrid form of dependency parsing, which uses valency theory to analyze the relationship between a verb and its arguments. They also mention the importance of considering linguistic features, such as part-of-speech tagging and named entity recognition, to improve the accuracy of word segmentation. Japanese word segmentation is also discussed, emphasizing the role of linguistic features and statistical models in achieving high accuracy. The authors highlight the need for language-specific adaptations to ensure optimal performance in word segmentation systems. The paper concludes by outlining related works and discussing future directions in this field. It emphasizes the importance of developing a near-perfect word segmentation system that can perform reasonably with minimal language-specific adaptations. The study presented in this paper focuses on resolving ambiguities in dependency parsing for Korean sentences using a statistical dependency parsing method. The parser selects a tree among all parses of a Korean sentence, utilizing simple constraints to reflect the syntactic characteristics of Korean and prevent overgeneration of dependency arcs. The parsing model's parameters are estimated using lexical dependency probability, which is a conditional probability measure of the head given multiple parts of the sentence. Linear interpolation is employed to estimate the parameter, and a parameter for modification distance probability is used with backoff smoothing. Experiments were conducted using the dependency-tagged KAIST treebank, consisting of 31,080 sentences. The parser achieved a relatively high arc-based FM measure on both the training and testing data. The results are presented in Figure 2, showing the parser's performance on the training and testing data. The parser's performance is also compared to 4 other models, including a baseline lexical dependency probability model, a model that distinguishes dependencies between adjacent words, a model combined with a triplet-quadruplet head candidate decision model, and a model based on bigram lexical dependency and distance between depending words. The proposed model does not perform well on the training set compared to the other models but outperforms them on the testing set. The results are presented in Figure 4, showing the comparison of the proposed model with the other 4 models. The study also explores a transition-based BILSTM parser for parsing at the JMO letter level, using Unicode decomposition to parse through each JMO letter. A sampled JMO letter parse tree is presented, demonstrating the parser's ability to parse at the JMO letter level. The study highlights the importance of considering the structural and syntactic characteristics of Korean in dependency parsing. The proposed model's performance on the testing set suggests its potential for improving the accuracy of dependency parsing for Korean sentences. However, the study also notes the limitations of the proposed model, including its performance on the training set, and suggests future work to improve the model's performance. Stratus study introduces a novel approach to parsing diagrams by leveraging JMO letters in the Korean language, enhancing the accuracy of dependency parsing. The method utilizes a BILSTM model with an innovative JMO architecture, which extracts JMO letters from any possible Korean character using Unicode decomposition. This process involves calculating the Unicode values for the head, vowel, and tail consonant, then applying the tanh function to create a new representation of the letters. These representations are concatenated with character-level lookup embeddings and fed into a BILSTM network. The network is trained end-to-end using a max margin objective, previously employed by Kipperwasser and Goldberg in 2016. The implementation of the BILSTM network utilizes a publicly available Korean treebank in the Universal Treebank 2.0. The use of JMO letters offers several benefits, including implications of the tense of the word and phonetic elements that could aid in speech processing. In Figure 2, Stratus Parser, Korean Net, outperforms other parsers that use word, character, and JMO letter features, achieving the highest test UAS of 95.17 and test LAS of 92.31. Stratus compares Korean Net with 5 different parsers: McDonald 13, Yara, K and G16, Dyer 15, and Ballesteros 15. Korean Net is plugged into a JMO architecture using the DieNet library. The parser uses 4 different iterations of features, including one with char, one with JMO, one with char and JMO, and one with all 3, word, char, and JMO. Notably, Korean Net uniquely utilizes JMO features compared to other parsers. This study compares the performance of various Korean language parsers, focusing on their feature representations, use of pre-trained feature embeddings, and POS tag implementations. The comparison is presented in Figure 5, where different parsers are evaluated based on their development and test accuracy with UAS and LAS metrics. The research also explores the limitations of statistical approaches for POS disambiguation in agglutinative languages like Korean, due to complex morphological structures. To address these limitations, a hybrid method combining statistical and rule-based approaches was proposed, as shown in Figure 6. This model integrates a morpheme dictionary to enhance morpheme identification accuracy, and it includes tasks such as morpheme segmentation, recovering original morphemes from spelling changes, and morphotactic modeling. In morpheme segmentation, input texts are scanned from left to right to match with morphemes in the dictionary, utilizing a tree-structured index for fast matching. Each variant surface form of the original morpheme has an independent entry in the dictionary, allowing for easy reconstruction of original morphemes from spelling changes. For morphotactic modeling, the study uses POS tags and morphotactic adjacency symbols in the morpheme dictionary. These provide information about grammatical functions and the possible combinations of morphemes, enhancing the accuracy of the POS tagging process. The hybrid model can be tightly coupled with generalized unknown morpheme guessing techniques, demonstrating a potential solution to overcome the challenges posed by agglutinative languages in POS disambiguation. The research paper discusses a hybrid tagging model for part-of-speech (POS) disambiguation in Korean, comprising a morphological analyzer with unknown morpheme handler, a statistical POS tagger, and a rule-based error corrector. The model leverages a morpheme dictionary to encode the full hierarchy of POS tags and morphotactic adjacency symbols for each morpheme, allowing for the identification and recovery of unknown morphemes. The statistical POS tagger utilizes the Viterbi algorithm to search for the optimal tag sequence, while the rule-based error corrector employs a transformer architecture to correct mistagged morphemes by consulting lexical patterns and contextual information. The performance of the statistical tagger is evaluated on 3 document sets with progressively degraded versions of the tagging mechanism. The results show a significant drop in performance between versions 1, 2, and 3, verifying the effectiveness of the unknown morpheme segmentation and guessing techniques. The hybrid tagger's performance is also tested, with version 1 incorporating unknown morpheme segmentation, guessing, and rule-based error correction, and version 2 omitting a posteriori error correction rules. The results demonstrate a mild performance drop between version 1 and version 2, indicating that the statistical tagger alone achieves state-of-the-art performance for tagging Korean morphemes. The paper also compares the proposed hybrid model with previous models, highlighting its advantages and disadvantages. The model's high recall and precision scores for various POS tags demonstrate its effectiveness in handling unknown morphemes. The authors conclude that each of the 3 methods discussed has its own strengths and weaknesses, with the hybrid hidden Markov model proposed by Gary et al. Showing the highest accuracy. Chinese word segmentation, CWS, is a challenging task due to the lack of word delimiters and the complexity of Chinese characters. 2 major difficulties in CWS are ambiguity and out-of-vocabulary words. Character-based approaches were dominant solutions for CWS in the past, including conditional random field, CRF, and maximum entropy modeling, MEM. CRF treats CWS as a binary decision task, labeling each character as a word's beginning or not, while MEM generates segmentation lattices from a single model. However, both methods have limitations, such as the inability to handle unknown characters and the need for explicit wordhood information. Recent approaches incorporating neural network (NN) techniques have proven to be powerful in dealing with CWS. However, NN architectures can provide accurate models but lack explicit wordhood information. The Wordhood Memory Module (WMSEG), proposed by Tian et al., combines a neural CWS approach with a wordhood memory module, which provides more wordhood information of the context. The WMSEG architecture consists of a text encoder, memory networks, and a decoder. The input sentence is first encoded, and then NGRAMS are extracted and passed to the memory networks along with wordhood information from a lexicon. The output is then passed to the decoder to predict segmentation labels. The innovative part of WMSEG is the wordhood memory networks, which model pairwise knowledge and offer valuable information between segmented contexts and their meanings. The model also introduces flexibility to integrate various encoders and decoders. Experimental results on SIGHAN 2005 and CTB6 datasets show that WMSEG outperforms other models, especially when using the wordhood memory module. The results indicate that the overall performance is improved when adopting the wordhood memory module, with higher scores on MSR, PKU, AS, CITIU, and CTB6 benchmark datasets. The WMSEG model uses a combination of BILSTM, BERT, and Zen encoders and softmax and CRF decoders. The experimental results show that the model achieves state-of-the-art performance on CWS tasks, especially when using the wordhood memory module. The results also indicate that the model can handle out-of-vocabulary words and provide more accurate segmentation labels. Here is the combined summary of pages 13 and 14 of the research paper. Word segmentation is a crucial task in natural language processing, particularly for languages like Chinese and Japanese, where word boundaries are not explicitly marked. The authors discuss various approaches to word segmentation, including the hidden Markov model, HM, and neural network-based methods. The HM is a stochastic algorithm that determines word boundaries based on the probability of word sequences. However, it has limitations, such as requiring a large word lexicon and struggling with out-of-vocabulary words. To address these issues, researchers have proposed hybrid methods that combine HM with character-level information, such as character tagging and word-level Markov models. One such hybrid approach is presented by Nakagawa et al., which uses a combination of HM and character-level information to improve word segmentation accuracy. This approach uses a lattice structure to represent word candidates and their corresponding probabilities. The lattice is constructed by labeling words with four main types of tags: beginning of a word, B, middle of a word, I, end of a word, E, and itself as a word, S. In contrast to traditional machine learning methods, neural network-based approaches have been shown to achieve state-of-the-art accuracy in word segmentation tasks. Kitagawa and Kamachi proposed a long short-term memory (LSTM) network for Japanese word segmentation, which incorporates character-type embeddings, character-based NGRAM embeddings, and a word dictionary. The LSTM architecture is designed to capture long-distance information and optimize performance. The authors present experimental results comparing the performance of different word segmentation methods, including HMM, hybrid HMM character-level methods, and LSTM-BASED approaches. The results show that the LSTM-BASED approach achieves the highest F1 score of 98.42. The authors conclude that each method has its pros and cons, with HM being easy to understand but limited in its ability to determine word boundaries, and neural network-based approaches achieving higher accuracy but requiring more complex training. Figure 11 illustrates a word lattice for a Japanese sentence, demonstrating the use of HM and character-level information to improve word segmentation accuracy. Figure 12 shows the detailed architecture of the LSTM network proposed by Kitagawa and Kamachi. The results of the experimental evaluation are presented in Figure 10, which compares the performance of different word segmentation methods on the SIGHAN 2005 and CTB6 datasets. The paper discusses the various word segmentation models for Chinese, Korean, and Japanese languages, highlighting their similarities and differences. In the early stages, statistical language models are widely applied due to their intuitive nature in determining word boundaries using probabilities generated by machine learning models. Neural network methods, such as RNN and LSTM, are also popular and have been shown to achieve the highest accuracy, particularly when combined with character-level information embedding. This approach is effective in handling problems related to unknown words. The authors also explore the application of these models in English processing, specifically in handwriting recognition, where spaces between words are not clear. The Chinese word segmentation method can help distinguish the boundaries of English words, demonstrating the universality of many mathematical methods of language processing. The paper further presents a comprehensive evaluation of word segmentation models on a wide range of languages, including Asian languages, Western and Eastern European languages, South American languages, and Middle Eastern languages. The evaluation results in Table 9 show that the proposed method outperforms UD-pipe in most datasets, with significant improvements observed in languages such as Arabic, Hebrew, and Hindi. The authors emphasize the importance of word segmentation in natural language processing, as it directly impacts parsing accuracy. They suggest that future work could involve exploring newer techniques for handling a broader array of Asian languages and analyzing the advantages and disadvantages of the new method compared to other methods discussed in the survey. The paper concludes by summarizing the contributions of each team member, with Matthew focusing on Korean word segmentation models and related work, Chen focusing on Japanese word segmentation models and future work, and Yexin focusing on Chinese word segmentation models and the significance of word segmentation in natural language processing. Here is the combined summary of pages 17 and 18. The authors provide an extensive review of existing research on word segmentation in various languages, including Chinese, Japanese, and Korean. They cite numerous studies that have employed different approaches to tackle this task, such as statistical models, machine learning algorithms, and rule-based methods. In the context of Chinese word segmentation, the authors reference works that have utilized maximum entropy modeling, conditional random fields, and word-hood memory networks. For Japanese word segmentation, they mention studies that have employed long short-term memory, LSTM, networks and hidden Markov models. Regarding Korean word segmentation, the authors highlight research that has utilized syllable pattern-based segmentation, hybrid part-of-speech tagging, and tied sequence-to-sequence multitask models. They also acknowledge the importance of considering linguistic features unique to each language, such as Chinese characters, Japanese kanji, and Korean morphological analysis. The authors further emphasize the significance of word segmentation in natural language processing, as it is a crucial step in various applications, including machine translation, sentiment analysis, and text summarization. They also note the challenges posed by languages with complex scripts, such as Chinese and Japanese, which require specialized techniques for word segmentation. The review of existing research sets the stage for the author's proposed approach to word segmentation, which is not explicitly stated in these 2 pages. However, the comprehensive survey of existing methods and the emphasis on linguistic features specific to each language suggest that the authors are poised to present a novel approach that addresses the limitations of previous studies.